So it's really my pleasure not to be back to pediatric rheumatology because I stayed all my life in pediatric rheumatology, but like Peter described himself, I'm also looking both sides, more at the adult size, but with key interest in the field of pediatric rheumatology. As you see on the slide, I come from France and Lyon specifically, because the IL-17, you have to remember, is a French discovery. So on my way from Dublin the other day, so the organizers were getting concerned because my slides were still on the plane flying with me, but not arrived here. So I felt, but I'm written already on IL-17. So see the title I used a few years ago, which was saying that now it's becoming important because switching from the adult to the juvenile field. So these are the points I would like to discuss. I will start to sort of show the translation, how this was discovered. Then, because we are discussing arthritis to some extent, arthritis has something to do with joint structure, obviously, and bone. At the same time, we are discussing systemic manifestations, so I will discuss vessels. That's critical, as discussed this morning by one of the parents. And also the effect on liver, because we heard a lot of liver manifestation. And the end will be targeting today and even tomorrow. So I will use the array, so the adult picture, but I don't see where this does not apply to some extent or fully to the juvenile arthritis. So something which is clear is that there is inflammation leading to destruction. And in the 80s, there was really a political debate, as you have today, saying, is there or not a role for T cells in arthritis? And IL-17 came just on time as sort of a T cell product, maybe showing the link between T cells, or some of the T cells, in the pathogenesis of chronic inflammation, to simplify. Today, this discussion is sort of useless, but years ago, that was a key point. And I use this very simple model, which is to take a piece of tissue, so keeping cell-cell interaction. And you see fully here that you have, in this section, a full immune system arriving there, a place where that migration is not supposed to be occurring. We don't know exactly why. So this has to do common with the discussion we are having on explaining the first step. But anyway, what we see is a migration. And when you have the migration of these immune cells migrating to vessels, accumulating, at the end, this is what you get. You get this immune system with full cell-cell interaction, interacting with the cells which were there from the first day. And these are so-called mesenchymal cells, or synoviocytes, the mesenchymal cells of fibroblasts from the synovium. And I hope you see clearly this picture, which shows cell proliferation. And cell proliferation, to simplify, this is joint swelling. And at the same time, you don't see the soluble factors which are produced. When I say everything looks easy afterwards, when IL-17 to be, the gene arrive in Lyon, bad start, so no effect on B cells, no effect on T cells, and people were saying useless, close the program. And then François Faussier here said, well, let's put that stupid molecule on top of synoviocytes. And that was the beginning of what is today the IL-17 story. So showing one thing, which is the induction of IL-6. So first the link with inflammation, the induction of IL-8, which is a factor key to attract neutrophils, so neutrophil biology. That was 1996, 1995. Then François produced the first blocking anti-IL-17 antibody. So we took, if I can go backwards, we took superinatants from these cell-cell interactions. And So that was the time of TNF, the time of IL-1. So no surprise, this massive induction of IL-6. But sort of surprise to some extent, good surprise, was that 2/3 of this activity could be reduced by blocking IL-17. So from the first day, there were hope, also questions. Questions, you see immediately the question, could a poorly active factor anyway contribute to such extent? So this is something which is important and goes back to the discussion IL-18, gamma interferon. So interaction, the team effort. So we discuss here team effort, which is to combine parents, us, industry. That's the team effort. And as a team, you know, sometimes you have a heavy bullet to pull. That's the other side of the team effort. But this is very critical. If you use small amounts of cytokines, that would be the case at the local site. So here you have modest effect of IL-1, TNF, and you can increase, obviously, the size of this list. No effect, modest effect, but in real life, at the site of the disease, you will get everything interacting to some extent together, and you get this massive effect. This is described as synergy, the team effect. And this marker here, this is a chemokine, which is now famous because this is a chemokine able to attract to some extent the immune system I showed on the first slide. So interacting immature dendritic cells and the Th17 cells. So as a summary for this first part, so keep in mind that IL-17 will act on all mesenchymal cells with different names according to where they are, inducing IL-6, that's inflammation, and inducing migration of neutrophils, activation of neutrophils. So again, IL-17 and neutrophil biology and disease. And CCL20 attracting the Th, so increasing then the production of IL-17 function. Also, IL-17 that you have seen not highly potent will make inflammation more inflammatory. And from there, switching from preclinical to clinical manifestations. And you have, as beginning of a list, the increased production of IL-1, TNF, IL-6, and the list can be longer. So I will discuss later the systemic effect, the effect on endothelial cells, and obviously now the bone effects. Life was easy. 1995. There was IL-17, there was the IL-17 receptor. And then, as a joke, I say, with time the family has been growing, as should be. So IL-17 is here, became now IL-17A. It's a dimer, homodimer, fully red. And of interest for clinical application at the end, it's the IL-17F. So the family, that's the IL-17 cytokine family. And on the other side, the receptor is not as simple as first described. So you have here the receptor, the old 95 receptor, which is now the array receptor. And the full receptor needs the interaction with the RC chain. And this, again, will be critical when it comes to targeting. So one slide for IL-17F, which is sort of step-by-step becoming in fashion because of clinical applications. So just to show, we are back to what I said before. So we take synoviocyte, we take fibroblasts, exposed to TNF, you get IL-6, to IL-17, modest increase, you combine the two, you get again more inflammation, more IL-6. But F is a stupid factor because F often has no effect, but again will make TNF more inflammatory. So from there, question being, do we need to target 8, F, the two together, or whatever? I will conclude on that. Now, switching to the local aspects. So I will simplify by saying there are two types of arthritis, either with destruction. This is rheumatoid arthritis, this is juvenile arthritis, this is psoriatic arthritis. Why do you get destruction? Well, because factors will induce destruction. But in fact, you get destruction for just one thing, because you don't get repair. So the lack of repair is absolutely critical. And if you are young, repair is not really repair, it's construction, being taller. So explaining why, if you have inflammation, you will be short because the repair activity is fully inhibited. So here's another disease that is used as an opposite situation, which is ankylosing spondylitis. There is sort of the same because the patient will lose bone, but they are stiff. They are stiff. Why? Because on ligaments of the spinal ligaments, they will get ectopic bone formation. So it's sort of the opposite. So the situation in destructive arthritis is get destruction because you can't repair. In ankylosing spondylitis, it's the same. You will lose spinal bone because of the inflammation. But you will get stiffness because there is some degree of repair activity. So the point is, how can we now justify blocking TNF to block destruction in a disease that is already making new bone? And the question is also the same for IL-17. So the bone structure in inflammation is sort of simple. It's, again, interaction. So you have interaction with osteoblasts, the bone-forming cells, and the other side, the bone-destroying cell. You need the bridge to have the full story. And this bridge will be activated with factors coming from monocyte, IL-1, TNF, IL-6 as official markers, but also from T cells, either through factors such as IL-17 going that way, or directly through cell-cell interactions. That's well known, well characterized, easy to show. You take pieces of bone from patients with arthritis in a test tube. You combine cytokines, you get more IL-6, and you get more IL-6, you get more destruction. Easy. And if you block cytokines, and using CTX, which is a marker of bone destruction, in a test tube you destroy ongoing bone destruction. And if you block cytokine, IL-17 here, but TNF, IL-1, who make the same, you reduce bone destruction. That's very simple to understand. But what about the ankylosing spondylitis? Showing that it's needed. We said good science is needed. Maybe that's one part. In the ligaments, you have mesenchymal cells. You don't have a full bone yet. So you have ligaments, and these ligaments the cells from the ligaments can't interact with osteoclast because that's not the place where this occurs. So very big surprise for us when we took mesenchymal cells from everywhere, put them with TNF in a medium-inducing bone, you see the red bone being formed with TNF. So big surprise. And again, IL-17 will increase this effect. So explaining why, in a situation where the crosstalk is not ongoing, well, bone could be produced. And trying to find the explanation, we found easily that there was a bridge effect. And again, this funny gene has just one thing, which is to do with the bridge. So now we are with something which is sort of simple. In array, in destructive arthritis, the bridge is there, so you get the full story with the full destruction. In the ligaments, in syndesmophyte, you don't have the full bridge, so instead of trying to destroy, you make a bone. So a single cytokine having opposite effects depending where they are. So effects on a vessel. So I indicated a few of those cells, so I want now to focus on endothelial cells as sort of the link between the inside and the outside of vessels. So back to this picture where we have now endothelial cells. Endothelial cells stimulated with cytokine will induce inflammation. That's one thing. Second thing, which will be on the next slide, are the effect on coagulation. And coagulation, to simplify, this is having or not having a myocardial infarction. So in test tube, we can induce myocardial infarction by mixing cytokines. This is tissue factor. Tissue factor is the top of the coagulation pathway. So we get, and we know, chronic inflammations leads to procoagulation. And again, we get these massive interactions. So procoagulation, that's the first step. Second step is platelet aggregation. So having already these two, you are near to reaching the level of thrombosis. And you lose twice because at the same time, you diminished the protective anticoagulation pathway. Two examples, thrombomodulin here and CD39. So now we have the effect, as you just described, the link between any type of inflammation, chronic inflammation, leading to surgery or death from cardiovascular event. And this is long-term effect on vessel, which is a key health issue, obviously, for further, not only research, but targeting. So there is another organ which is of importance. This is liver. So liver is a big thing. So acting on liver will have big effects. So I mentioned the effect on vessels. And now I will describe this part, which is the effect on liver, leading also to the now link between inflammation, systemic inflammation, just simplified as CRP. And if you have just a modest increase in CRP, you will die sooner from cardiovascular events, to simplify. And it doesn't matter what you eat. I refer to foie gras. No effect. Keep eating foie gras. So anyway, so these are hepatocytes. You see, when we combine cytokine, we induce inflammation, we induce massive IL-6 expression, massive IL-6 production. This is a classical view. IL-6 is a marker of systemic inflammation. But what about blocking IL-6? Tocilizumab being the example. So we have here the effect of IL-6 on liver, inducing CRP, which is fully, completely inhibited when blocking the IL-6 receptor. And it is copy and paste for the action of TNF IL-17. So simple, TNF IL-17 will induce IL-6, and that will induce CRP, as expected, I would say. Something which is different now, when we look at cells, so here I'm back to neutrophils, then it's just the opposite. So we have IL-8, measure here expression and production, and you see clearly that this massive effect is not inhibited when blocking IL-6. So you have two stories, one which is simple, the systemic effect on soluble markers. CRP is just one of them. Cytokine will go through IL-6, leading to systemic inflammation. But the cellular effect of inflammation are not under IL-6 control. So reasons to do this research is obviously to move forward. So this is where we are in terms of targeting. So 1995, 1996, this is blocking IL-17 that became today IL-17A. Two molecules, secukinumab developed by Novartis and ixekizumab developed by Lilly, target IL-17A. The IL-17 receptor, in fact the RA chain, not the RC, targeted by brodalumab, which was started with, it's a long way, by Amgen. So have a look. These results are based on patents from 20 years ago. So when we say everything goes so fast today, 20 years to... Anyway, so IL-17A and F with a molecule blocking a common structure on both A and F, so molecules already in clinical trials. Back to targeting TNF and IL-17, two ways, sort of simple, which is having on one side a TNF inhibitor and IL-17 inhibitor. You can play with which one first, which concentration, or having use of modern technology, which is use a so-called bispecific inhibitor with two arms, one for TNF, one for IL-17. So to give the full picture and not my contribution, you can also work upstream. So either targeting the transcription factor for the Th17 differentiation, this is ROR gamma T, ROR C, or target IL-23 that we had seen on previous slide, which is one of the many factors inducing the Th17 pathway. So where are we today in terms of targeting? In skin inflammation, never seen before. You have the disease first, you give the drug, the disease is gone. So leading to the registration early 2015 for secukinumab and early this year for ixekizumab. Psoriatic arthritis and ankylosing spondylitis, so it's still ongoing. I use that word interesting because skin inflammation, it's fully gone. You have arthritis, difficult to have the arthritis being gone so easily. So in RA, results are more complex because, again, we have massive heterogeneity, very good, very bad responders. So the need, obviously, at what was said before, of selection of patients. Interesting results also in multiple sclerosis. And sometimes life should have been easy. It's not as easy. In Crohn's disease, where there is inflammation, so obviously expression of IL-17 is even worse than nothing because in some patients they've got increased disease activity. And the point is to understand this surprising or not result. So summary. So remember, IL-17 alone does not much, but will sort of amplify the immune response, often neutrophil-driven at the local site, so acting on the local inflammation in a long list of conditions, but also critical to take into account at the systemic level. So key point interacting, IL-17 interacting with cytokines. Something I've not shown, but I feel is critical, is the understanding of chronicity. We know too well today that if we block with cytokine inhibitors, cell inhibitors, an inflammatory disease, that's nice. That has been the progress. But if we stop the inhibition, often just wait and months later, the disease is back. So remains to be understood chronicity and exposure of mesenchymal cells, synoviocytes, skin fibroblasts to this factor will induce one thing which is critical, which is this cell will forget one thing, which is to die. And not dying, the immune-induced disease, not sensitive to regulation, is now ongoing. So it goes to common sense, which is early is, as always, better. And I've listed some of the ongoing results. You have seen more molecules coming. I listed just a few of them. And the list of conditions to be tested is just increasing. Thank you.